Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will complete our discussion on the combined periodic oscillations, and in the later half of this discussion I am going to introduce a very interesting topic on energy conservation. Okay, so let us continue our discussion on linear oscillations. And in this particular quick discussion I am going to go back to my scenario of two masses which are being attached by three springs, and we want to see the combined motion. Okay, so in this case, let me change this problem a little bit. So here we have again two rigid supports. Let me call this as and then we have two masses which are sitting at a distance, let's say A, and then this is also A and this is 2A, right? And so what we have is, we have the masses, let's say this is 2m and this mass is m, and then these masses they start to oscillate. And we want to find the combined frequency of this periodic oscillation. Okay, so what have we got here is let us look at these two particles. So we have two particles of let's say P and Q. So this is P and this is Q. Two particles P and Q of masses m and 2m and m. So P is of mass 2m and Q is of mass m. They are attached to a light spring. And that is stretched. Right? Stretched. What do I mean by stretched? The string is stretched and it is performing some vertical motions due to the tension in the string, right? And then the particles are going to undergo, P and Q undergo vertical oscillations perpendicular to the equilibrium line of the string, okay, and we want to find the normal frequency, the normal mode form. Basically, what is the normal mode form? We are trying to find the solution, that is the x, and that is the displacement. So the normal mode forms and the general motion of the system. So that is what it is asking us to find. Okay, we have already seen a very similar scenario of two particles attached with three strings, and we have looked at the general motion of those system. So using that system in the previous module as my reference, I can quickly write down the equation of motion for this string mass system, right? Very similar to the spring mass system. So we have the equation of motion. The equation of motion is as follows. We see that we have 2 times mx double dot is equal to minus T naught. So T naught, so both these masses they are getting stretched, so you will have some tension T naught, right? And the second mass is being stretched like this, and then eventually this. So we have some T naught, right? So T naught is the net tension. So the first equation of motion is for the mass 2m. So 2m x double dot is T naught by A times x dot, well, times x plus T naught over A times y minus x. So notice that the terms on the right hand side have a very similar setup compared to the spring mass system studied earlier, where now my restoring force is being replaced by the tension in the string, right, where A is the equilibrium length of the string. So this A is the equilibrium length of the string. Okay, and then similarly the second equation of motion is m times y double dot is equal to minus T naught y minus x over A. So positive here, negative here, and minus T naught by 2A times y, because the total length in the third string is 2A. Okay, and then all we have to do is to start introducing some common terms, reduce the number of parameters, and look at the system in the reduced form. So we can again write this equation in this form. So 2x double dot plus 2n square x minus n square y is equal to 0, and 2 times y double dot minus 2n square x plus 3n square y is equal to 0. And from here we find that my normal mode forms are A cos omega t minus gamma and y is equal to B sine omega t minus gamma, right? And from here we can once we have assumed this form of the solution, we can plug it back into our system, and we see that our matrix looks as follows. We have 2n square minus 2 omega square minus n square, and we have minus 2n square, and the last term is 3n square minus 2 omega square. Okay, and times A and B, the vector, this is set equal to 0, 0. So again we will have to say that we want non-trivial solutions. For non-trivial solutions we have to set up the determinant of this matrix to be equal to 0, and we solve for the unknown omega in terms of the known n. Well, what is n? Here n square is T naught by ma. Okay, so then we get two solutions. Omega is n over square root 2 and omega 2 is square root 2n, and we see that for omega 1, which is the slow root, so for omega 1 we find that x comes we have that A comes out to be equal to B, let me call this delta, and the solution comes out to be x is delta 1 cos of cos of omega 1 times t minus gamma, and y is delta 1 cos of omega 1 t minus gamma, because we call this as delta 1, right? Both the amplitudes come out to be equal when we solve the system. And similarly for the fast mode, we see that A comes out to be equal to 2b. A is 2b. Am I right? A is 2b. Right. Well, A is B. It comes out to be B is minus 2a. So then the solution comes out to be x is equal to delta 2. Let me call this as delta 2. So x is delta. So B is So x is delta 2 cos of square root cos of omega 2 times t minus gamma. Let me call this as gamma 1 and this is gamma 2, and y is equal to minus 2 delta 2 cos of omega 2 t minus gamma 2. And then when we add these two solutions, we get that the total solution is x is delta 1 cos of this quantity here and plus delta 2 cos of this quantity here, and similarly y will have the corresponding solutions in terms of delta 1 and delta 2. And before we wrap up this discussion of this these string mass system, we see whether the system is periodic or not. Again, note the ratio of omega 1, the ratio of the frequencies omega 1 by omega 2. This comes out to be 1 over square root 2 divided by square root 2, and this is going to be 1 over 2. So this is a rational number. This is a rational number, and we expect that for this rational number, we expect that the system is periodic. Now, the question is, if the system is periodic, what is going to be the period of the system? The period, so periodic with period given by the slow mode, okay, the slow mode. So t is going to be 2 pi divided by omega 1, which is 2 pi divided by n over square root 2, right? So that is a slow mode, because that's the larger of the two numbers coming from the fast mode and the slow mode. So the net period will be the period given by the slow mode. So that completes our discussion in this system of string mass attachment. And now let us move to a more interesting and a very alternate way of viewing the kinematics of the particle, namely the viewpoint of the energy of the system. Okay, so let us talk about the kinematics from energetic consideration. So we talk about the so-called energy conservation or energy consideration. Energy consideration. Okay, so the key concepts, well, we'll briefly cover this this topic for about up to the end of this module, and we'll continue later on. So the key concepts of this topic are going to be conservative fields, and then potential energy, and energy conservation, potential energy and energy conservation. Okay. So what we have is, suppose the energy principle. Let us go back to our discussion starting from the so-called energy principle. So what does this say? We are going to derive the energy principle by the Newtons, through Newton's laws of motion, right? So the problem says that we have a particle P of mass m. Particle P of mass m is moving. It moves under the influence of force F. Okay. So what have we got? So then we have m dv dt. M dv dt is F bar, right? And from here we can rewrite this equation of motion as m times dv dr. Well, we would like that this is going to be well, hold on. So this equation of motion we can rewrite by taking a dot product with respect to v. So we take a dot product. This whole thing is taken a dot product with respect to v. We see the equation changes as follows. So this is m v dot dv dt. This is equal to F dot v, right? And now notice that I can integrate the left hand side. The left hand side is half mv square, right? So that is half m. So this is what we have. The left hand side is the derivative, the time derivative of half mv square, and of course the right hand side is F dot v. This is still the Newton's second law. But now when we integrate, we see that what we get is half mv square, is my so-called term t, where we denote T as the so-called kinetic energy. Okay. So this particular equation is dt is equal to F dot V. So once we integrate, we find that integration from, let's say, time t1 to t2, and we see that this is going to be the change in the kinetic energy t2 minus t1, and this is equal to integral from well, so this is f dot v dt. So from t1 to t2, f dot v dt. Notice that the left hand side is the change in the kinetic energy, and the right hand side, so this is the change in the kinetic energy. So kinetic energy being Ke, so this is the change in the kinetic energy, and the right hand side is the work done, right? So the work done is equal to the change in kinetic energy, is what my energy principle says. Energy principle. Okay. Okay. So now let us look at a quick application of this energy principle. So the problem says, before moving ahead, I just want to briefly mention that energy principle and equation of motion are identically equal. That is what we saw in the derivation. But energy principle is slightly, has slightly lower advantage, because energy principle can only give us scalar quantity like work done or the speed of the particle and so on. It does not give us vector quantity like the equation of motion, right? But that is another way of finding the variables, that is via energy principle, as we will show you in the next example. So the problem says a man of mass 100 kg, that's quite a heavy for a man, can pull on a rope with maximum force, can pull on a rope with maximum force equal to 1/5 of its own weight, equal to 1/5 of its own weight. And then in a competition, the problem says that in a competition he pulls a mass of 1600 kg, on a smooth horizontal floor, from rest for 12 seconds before stopping. Okay, the problem says find the total work, that is the first part, find the total work done by the man, and the second part says that we need to verify the energy principle. Okay, so let us see what we have. So we have the mass of the man is given to be 100 kg, and it can pull on a rope with maximum force equal to 1/5 of its own weight. So we can take g, our acceleration due to gravity, to be roughly 10 meters per second square. So in that case, the weight of the man comes out to be, the weight W, well, I should not say W because I will use it for the work done. So the weight is m times g, which comes out to be 100 times the acceleration due to gravity. So this is roughly 1000 newtons, okay, in SI system. Now the man is exerting a force which is equal to maximum force equal to 1/5 of its own weight, which means that the force being exerted is 200 Newton, right? And then it pulls a mass of 1600 kg on a smooth horizontal floor from rest for about 12 seconds, right? And we have to find the total work done. So the total work done is F dot V, and F is given to be 200 Newton, and we have to find what is V. So what we have is, the total work done is integral. So it has to be integral over the time t from 0 to 12 seconds, right? And so this is integral from 0 to 12 seconds, 200 times v. But now what is v? So v is, again, if we look at our equation of motion, we see that my acceleration a is f over m, or we have that dv dt is equal to 200 divided by 1600, or this is equal to 1 over 8, right? Or we integrate this, we find that v is equal to t over 8, because at t equal to 0, the man starts from rest. The initial condition is already given. So we find that v is t over 8, we plug it into this integral. So this is t over 8 times dt. And then when we integrate this, we find that this is coming out to be 1800 joules of work done by the man. Now the second part says that we need to verify the energy principle. Basically we have to show that the work done W is equal to the change in the kinetic energy. So work done is already found to be 1800 joule. Now let us find the change in the kinetic energy. So this is equal to the kinetic energy T2 minus T1. So this is equal to half the energy when the velocity was at 12 seconds. So V12 square minus when the kinetic energy when the velocity was at time t equal to 0 seconds, right? Well, that is 0. And then V12, so V12 is the velocity at 12 seconds. So V12 was t over 8. This is evaluated at t equal to 12, and that comes out to be 1.5 meters per second. We plug it back and we see that the change in kinetic energy comes out to be exactly 1800 joules. 1800 joules. And hence this is also equal to the work done. So hence we have verified our energy principle in this scenario. So let us wrap up our discussion in this module, and in the next module I am going to continue talking about energy conservation and the energetic consideration viewpoint of viewing the motion of the system. Thank you very much, and thank you so far for listening.